Previously on the Math Club.
Say, Noah, when this episode's done, you want to get some cheese and crackers? Oh no, you just reminded me. Sir Barnabas, he's been waiting all this time. Sorry, Pete, I gotta go. Bye, everybody. Bye, Barnabas! I'm coming, Sir Barnabas. I'm so sorry. Sir Barnabas? No, Noah, what's wrong? Oh, we left Sir Barnabas over here while we were recording our last episode on imaginary numbers, and now he's not here. I'm not sure where he's gone off to. Oh, yeah, your childhood imaginary friend. Yes, Sir Barnabas Cheese and Crackers. I've totally lost him. Dude, this is not a big problem. It isn't? No, not at all. Sir Barnabas is an imaginary friend, so just imagine that he's right here with us. Yeah, that's a great idea. Hang on a second. Sir Barnabas, there you are. See? Hang on a sec, Pete. He's upset about something. What's wrong, Sir Barnabas? What? No. Well, don't listen to him. What's wrong? He's mad at me for leaving him behind, and he's been getting some pretty crummy advice from his friend, Lord Flappenquack. I almost don't want to ask, but your imaginary friend has another friend? Yeah, but Lord Flappenquack is totally irrational. He wants to be Sir Barnabas's only friend, so he's telling him that I abandoned him on purpose. No, calm down, Sir Barnabas. I would never leave you behind intentionally. What? Pete, he wants to hear it from you. From me? What? Why? Because you're also real. Sir Barnabas is a complex guy, and he trusts real people, which is why we usually get along so well. Come on, Pete. Tell him I'm still his friend and that I would never want to make him feel neglected. Okay. Sir Barnabas? Pete, who are you talking to? Sir Barnabas is over there. Oh, right. Sir Barnabas, please forgive Noah. I'm the one who made him leave you here while we recorded our last episode. As soon as we were done, he ran right back over here to find you. Did that work? What do you say, Sir Barnabas? Oh, shucks, I missed you too. Yeah, we're good. Well, you can't imagine how relieved I am. And speaking of imagining, all of this talk about friends who are imaginary, complex, irrational, and real is reminding me of the different number systems. In our last episode, we talked about the imaginary and complex numbers, but they're really not the only kinds of numbers that have some kind of imaginariness to them. They're not. Not at all. Sir Barnabas, would it be okay with you if Noah and I talk about this for a while? As long as I promise he'll be back as soon as we're done? He says it's okay. He may be complex, but part of him is pretty realistic. Well, great. So do you remember the beginning of our last episode? You were convinced that the line between real and imaginary numbers was pretty sharp. Like, some numbers were definitely real, and the imaginary numbers were definitely not. Yeah, but I think I have a better sense now that the line isn't quite that sharp. I still do think that some numbers are a lot more real than others, though. Okay, that's cool. Then I have a question for you. How real is the square root of 2? Like, what actually is it? Well, the square root of 2 is an actual positive number, but I see what you mean because it's irrational. It never ends, so you can't actually have any physical thing in the amount of the square root of 2, can you? You can't have like square root of 2 gumdrops or square root of 2 gallons of gas in your car, right? Well, actually, I would say you can have square root of 2 gallons of gas in your car. And the way you would is suppose you have 2 gallons of gas in your car and you're driving your car around and it is steadily consuming gas in some continuous fashion. And maybe an hour later you look and you go, oh, now I only have 1 gallon of gas in my car.
Well, if you started at 2 and you continuously dropped down to 1, at some point you must have passed the square root of 2. So there was a moment, an instant, when you were exactly at the square root of 2. And then you kept going.
But I'm going to interrupt there and say, how could I have been exactly at it? If the actual square root of 2 number is an irrational decimal that never ends, there isn't an actual amount that definitively is the square root of 2 gallons.
Well, there's no rational number equal to the square root of 2, but that doesn't mean there's a gap in the real number line, that the square root of 2 doesn't exist. And therein lies the challenge. What exactly are real numbers? What I want to say is that the real numbers, and specifically I mean the irrational ones, are the most imaginary numbers of all. Like you just said, an irrational number has an infinite decimal expansion. And that expansion is non-repeating and usually has no pattern to it. So what exactly do we have here?
Hey, what is this? What's this?
Yeah, I mean, like when you look at a rational number and you try to figure out where that number goes on the number line, there's an exact point on the number line where that rational number goes. But if you tried to put an irrational number like the square root of 2 on the number line, there's no exact point where that quantity goes on the number line. It's more of a kind of a fuzzy range, right? Like it's between this and this, but you never actually can narrow in on the exact point on the number line where that needs to be.
I like that expression, fuzziness. Let's dive into it a little bit. We know the square root of 2 is bigger than 1 and less than 2. Great. But let's be a little more precise. How about its decimal expansion? How does it compare to 1.1, 1.2, and so on? What would be the next decimal place?
Oh, I see what you're saying. 1.2 times 1.2 is 1.44. Obviously, because it's like 12 times 12. So that means 1.3 times 1.3. What's 13 times 13? 1.69. So we're closing in on 2. 1.4 times 1.4 is going to be 1.96. 1.5 times 1.5 is going to be 2.25. So it's going to be somewhere between 1.4 and 1.5.
Right. And so you've pinned it down. It started out in between 1 and 2. 1 being a lower bound and 2 being an upper bound. And then you pinned it down to 1.4 as a lower bound and 1.5 as an upper bound. Both 1.4 and 1.5 are rational numbers, right? One of them, you could write it as 14 over 10 or 7/5. And on the other hand, 1.5 is 3/2. So we've got 2 rational numbers now, which are closer to the square root of 2 than the 2 whole numbers that we started with, right? So, right, you could continue in this process by finding rational numbers that are closer and closer and closer to the square root of 2. But you're never going to get there.
I get what you're saying, but just to be clear, back to the gasoline metaphor, I think what we're saying is, as I'm using gas, at some point after I have 1.5 gallons and before I get to 1.4 gallons, at some point I'm going to have the square root of 2 gallons of gas in my car. But am I also right in saying there would have been no point where I could have turned off the car and said, I right now have exactly square root of 2 gallons in the tank? That I would never be able to do, right?
Well, now we're getting really real here. Actual cars and actual tanks of gas. Like, what kind of car do you even have?
Well, as it turns out, I have a hybrid, which means it uses part real gas and part imaginary gas. We're getting very complex here.
Okay. I think you're right about the exact point when you have that amount in the tank, but it's not because the square root of 2 is irrational. You know, I keep saying things like the continuous process by which the volume decreases, but I'm sure listeners who know chemistry and way more about science than I do.
Chemistry?
Yeah, chemistry.
They could very reasonably say, but gasoline is comprised of some finite number of discrete molecules, so you're not dealing with continuous quantities anyway. And when I say there's a square root of 2, quantity in the middle, I'm really relying on a property of the real numbers called completeness. Essentially, it means there are no gaps. The real number line is a continuum. It doesn't have any holes in it.
All right, that all makes sense. But what are irrational numbers then in this context? I'm still confused.
So I think the key is to kind of turn our thinking inside out. So instead of thinking about rational numbers as approximations to some pre-existing irrational quantity, let's say that these approximations are the irrational quantity. And what I mean by that is this. Let's take an infinite sequence of rational numbers that's headed toward a gap in the rational number line and say that that sequence is itself an irrational quantity.
Wow, Pete, that is imaginary. Maybe I should talk to Sir Barnabas about this a little later since he's imaginary too. Maybe he can explain this to me.
I know it sounds crazy, but hear me out. For the square root of 2, let's suppose I have this sequence: 1, 1.4, 1.41, 1.414, etc. That sequence is heading straight to the square root of 2. And in fact, everything we need to know about the square root of 2 is already encoded in the sequence. So this is how mathematicians have defined irrational numbers, as sequences just like this one.
Okay, well, you've done a really nice job convincing me that imaginary numbers aren't so imaginary, and also that irrational numbers aren't totally fake. Is there anything else I should know?
Hey, that is not exactly what I meant to do.
Well, one thing that you just showed me is that even non-imaginary numbers, like the square root of 2, share some qualities with the imaginary numbers. But what about plain old positive integers like 1 or 5 or 93? There's nothing imaginary about them, is there?
Of all the numbers we've talked about, the positive integers definitely seem the most real to me. I happen to be holding a glass of water, for example, so there's a representation of the number 1, the 1 glass. The hand I'm holding it in has 5 fingers, and over on my desk, I can see a stack of 5 books. So there are 2 different representations of the number 5.
Oh, and for a representation of 93, we can think about the year that we met, 93.
Yeah, that's true. That's true. So we cross a line of imagination when we abstract away from these particular representations and move toward a general conception of number. My hand, the books on the desk, they both have something in common, right? Let's call it fiveness. 5 fingers, 5 books, fine. But what is this underlying fiveness anyway?
You know what? This is making me think of our very first episode, Much Ado About Nothing, when von Neumann built up the natural numbers using different combinations of the empty set.
Oh, right. That's actually a really good point. Von Neumann came up with this way to associate a special set with each of the natural numbers, right? So 0 corresponds to the empty set, 1 corresponds to the set that contains the empty set, and so on. Each set has a certain number of elements in it, and that's the number it represents. And this allowed him to define the natural numbers in terms of those sets. Everything was taken care of. Put into this context now, even the positive counting numbers, like, they seem at least a little imaginary.
And I'm guessing that the negative numbers seem even more imaginary than that, right? But now that I'm thinking about it, how would a mathematician even describe the realness of negative numbers?
Well, here's a very von Neumann-y way to do it.
Von Neumann-y, is that a technical math term?
Let's just say that it is, okay? Well, we've been talking about the number 5. So let's talk about its partner, negative 5. Since we can't just point to a set that contains negative 5 elements, we need a new idea.
Right. Because there's no such thing as a negative quantity in the real world.
Yeah. Well, at least you can't have a literal negative quantity, but you can use a metaphor. So if I borrow $5 from you, then I can think of that debt as a representation of negative 5. So here's an idea. Let's represent integers as pairs of natural numbers. The first coordinate will represent a positive quantity, and the second coordinate will represent a negative quantity.
So, for example, if we use the pair of numbers 7, 4, then 7 would be a positive quantity and 4 would be a negative quantity?
Yeah, so this pair of natural numbers is a way to represent the number 3. That's because we're thinking of 7 as a positive amount, 4 is a kind of canceling negative amount, and when I bring those two together, what I would be left with is 3. So you were asking earlier about honest to goodness negative integers. What do you think we could do to this pair of natural numbers to make it negative?
Well, what if we swap the order of the coordinates? If the positive quantity were 4 and the negative quantity were 7, then that would be a way to represent negative 3.
Bam, you got it. That's right. If we had 4 representing a positive quantity and 7 representing something negative, there would be a cancellation. The 4 positive would vanish and we'd still be left with 3 negatives. That's how we represent negative 3.
Okay, but now I have a question. Wouldn't that mean that 3, 6 also represents negative 3, and so does 2, 5, and come to think of it, so would infinitely many other pairs?
Yeah. In fact, any pair whose first coordinate is 3 less than the second coordinate, that's a representation of negative 3. And you could keep reducing those coordinates down until one of the two numbers in the pair is 0. In this case, it would be 0, 3. And that's the simplest way to represent integers, at least in this notation. In fact, it's a lot like reducing a fraction to lowest terms.
Okay, so integers are made up of two parts that are positive and negative, which is kind of similar to how complex numbers are made up of two parts that are real and imaginary.
Yeah. And you know what? Rational numbers are made of two parts also, a numerator and a denominator. This is a pretty interesting recurring theme in mathematics. You form new objects from pairs of familiar objects. But there is one kind of number that we talked about today that is very different, and it doesn't fit into this pattern. It isn't just formed by taking two parts and putting them together in some way.
Well, which kind of numbers do you mean? Wait, actually, let me guess. The irrational numbers?
Yeah, exactly. They're definitely not just pairs of rational numbers or anything like that. In fact, it takes infinitely many rational numbers that are put together in a special kind of sequence, right? Those sequences target the gap. And that's what an irrational number is. Yes, it is built from familiar parts, but infinitely many familiar parts that behave in a certain special way. So very different, right?
Right. So now that we've talked about all of the different number systems,
actually, we haven't talked about all of them.
what do you mean? We've talked about positive and negative whole numbers, so that covers the natural numbers and the integers. We talked about rational numbers and irrational numbers, so that covers the real numbers. And we talked about imaginary numbers, so we covered the complex numbers. What else is there?
Well, do you remember that guy Hamilton from our last episode? After working with the complex numbers, Hamilton started looking for a way to extend them into 3 dimensions.
Do you mean that he wanted to add like a z-axis to the real x-axis and the imaginary y-axis?
Yeah, and that's because the physical world is 3-dimensional. He wanted to do physics with something like 3-dimensional complex numbers.
Interesting. Was he successful? Did he find them?
He did not. And that's because later mathematicians proved that no such system can exist. For starters, the only possible dimensions that can work are powers of 2. So 1, 2, 4, 8, and so on.
So wait a minute. 3-dimensional numbers are out, but 4-dimensional numbers are all of a sudden a possibility?
Well, have you ever heard about the Quaternions?
Oh, yeah, I think so. Weren't they that species on Star Trek that had evolved so far beyond us that they didn't even have physical bodies anymore?
Oh, they definitely are not bodiless future space aliens. Here, let me put it this way. A quaternion is a number that looks like a complex number, but it has two additional imaginary parts. And those parts come from two new square roots of -1.
Hold on. There are new square roots of -1? You mean besides I and negative I?
Oh, indeed. They are called J and K.
Now I feel like you're about to say JK.
No, these are real imaginary numbers.
Oh, real and imaginary, huh?
No, not real. Listen, I'm not kidding. These are actual imaginary numbers, and we do in fact call them J and K. And when we put them together with I, we can use addition and multiplication to build, well, an infinite number of brand new square roots of -1.
Oh, of course. There are infinitely many square roots of -1. No problem. We'll just check them all into Hilbert's Hotel.
Well, actually, Hilbert's Hotel is a little too small for all these square roots of -1s. But before we lose our minds, let's rein in our imagination and get our feet back on the ground.
Good idea, Pete. I think Lord Flappenquack was starting to flip his wig.
Oh, poor Flappenquack. Okay, so these new roots, J and K, give us two new coordinates to work with, right? So that means that an example of a quaternion would be something like 1 minus 2i plus 3j plus 7k. And since there are a total of 4 coordinates, the space of quaternions is 4-dimensional.
That first part, 1 minus 2i, looks just like a complex number. In fact, it is a complex number, isn't it?
Yeah, you're right. It is.
And the second part, 3j plus 7k, that also seems really close to being a complex number too.
Yeah. In fact, we can actually think of quaternions as being built from pairs of complex numbers. And that means that the quaternions also fit this pattern of pairs that we talked about a few minutes ago.
All right. That doesn't seem too far out there, but now I have a question. How are we supposed to picture these numbers? I mean, I'm just not sure how to visualize a 4-dimensional number.
You're just not thinking fourth dimensionally.
Well, would you believe me if I told you we have to use our imagination?
Would you believe me if I told you that's the same thing Sir Barnabas would say?
I would. I think I would believe you. You know, it's actually really pretty tricky. I think the best we can do is reason by analogy and make comparisons to familiar lower dimensional situations. For example, have you ever drawn a 3-dimensional shape like a cube on a piece of paper?
Oh, sure. And I bet most of our listeners have too. You end up with like a perspective drawing and you have to imagine it's actually 3-dimensional.
Right. And what you just described is a kind of projection of a 3-dimensional shape onto a 2-dimensional plane. And that's something we can do with the quaternions as well, either by projecting them into 3 dimensions, or we could go all the way down to 2 dimensions and draw them on a piece of paper as well.
You know, as an EdTech instructional coach, I have to say, this sounds like something technology could really help with.
Totally. And, you know, I do know of a very cool video by 3 Blue, 1 Brown that's all about the quaternions and how to visualize them. So why don't we go ahead and put a link to it in the show notes and also on Twitter.
Cool. Now, can we go back to Hamilton for a second? How did he discover or invent, or maybe I should say, how did he imagine the quaternions in the first place?
Yeah, well, you know, he'd been looking for something like them for close to a decade, but when it finally clicked, there's a really cool story about that moment. So William, that's Hamilton's first name, by the way. William was walking with his wife, Helen, near the Royal Canal in Dublin when he was suddenly struck by this flash of insight. And he was so moved by it that he carved a formula into Broom Bridge. That's a bridge that spans over the canal. Well, The original carving isn't still there, but in 1958, a commemorative plaque was installed in the bridge's stonework. And here's what that plaque says. Here, as he walked by on the 16th of October, 1843, Sir William Rowan Hamilton, in a flash of genius, discovered the fundamental formula for quaternion multiplication. And then it gives a formula. I squared equals j squared equals k squared equals ijk equals -1. And it goes on, and he cut it into a stone of this bridge. So I think that's so cool. 180 years ago, Hamilton has this insight, and he commits an act of vandalism against a bridge, and now you can go to Dublin and see a plaque.
That is pretty cool. You know, if I ever had a brilliant flash of genius insight while walking with my wife, the closest bridge to me is all the way in Oakland. I'd have to walk about 40 miles to be able to scratch my brilliant insight into a bridge, so I don't think I'm going to be doing that.
Dude, don't you actually live close to a town called Dublin?
I do, but not the one that Bono comes from.
Well, I'll tell you what, if you ever do have a brilliant insight, go ahead and give me a call. It'll be easier, and I'll pat your back and high fives and all that.
And so you know what I'm thinking now? Now I think that Sir Barnabas is going to need to add one more friend to his social group. We have real friends, imaginary friends, we have irrational friends. And since the fourth dimension is time, now he's going to need to befriend a time traveler from the future.
I don't want to rain on your little parade here, Noah, but actually the fourth dimension isn't time. It's just a fourth spatial dimension.
Oh, I see. So the impression that I'm getting from all this is that the Quaternions are every bit as real and as imaginary as the complex numbers. Does that seem like a fair thing to say?
Yeah, I think so. The Quaternions really are an extension of the complex numbers, but it's not all that radical of an extension. For example, inside the complex numbers, we have imaginary numbers, and together they form a one-dimensional line, the y-axis. And similarly, inside the Quaternions, we also have imaginary numbers, and together they form a larger three-dimensional subspace.
Ah, subspace. I knew this was from Star Trek.
Dude, are you stuck in a subspace bubble? Because I'm beginning to think this isn't getting through to you. Speaking of subspace bubbles,
The singularity that created some kind of subspace bubble around the ship.
and I can't believe I'm actually running with this analogy, but there is a kind of subspace bubble here in the Quaternions.
Ooh, there is?
Yeah. Do you remember when I said there are infinitely many square roots of -1? Well, if we look at them as a single geometric construct, they form a sphere. And in fact, it's the unit sphere inside the purely imaginary subspace that we're talking about. So yeah, totally space bubbly.
Weird. But like so many other weird things you've told me about since we started the math club, it's also very cool. And you know, Pete, when we started, not this episode, but the episode before this one, I was pretty sure that I knew that imaginary numbers were completely imaginary and all of the other numbers weren't. And I think that you've done a really good job of kind of turning me around and showing me that imaginary numbers aren't necessarily that imaginary, and that really all numbers do have some kind of imaginariness to them.
Yeah. Well, first of all, thank you. And actually, it was our conversation together that brought all this out. I think the thing I want to emphasize in all of this is the power of human imagination and the role that it plays in constructing the mathematical world. It just never ceases to amaze me.
Yeah, me neither. Pete, would you like to tell our listeners how they can get in touch with us if they have any questions or want to suggest topics for future episodes?
Yeah. Math Club, reach out to us on Twitter. Our handle is @Math Club Podcast. As always, you can send us an email. Our email address is mathclubpodcast@gmail.com.
And if you enjoy the Math Club, do us a favor. Tell someone else about the podcast. Word of mouth is the absolute best way to help grow our community and add new members to the Math Club. So share the podcast with a friend or colleague who you think would enjoy listening.
You know why I'm not saying anything right now, Pete? I'm imagining that I just said the most brilliant closing line that I have ever had on an episode.
That's one of those cool ideas that you should call me about.
All right, so to Sir Barnabas and Lord Flack and Quack and all of the people out at the Math Club, we will catch all of you later.
See you next time.